Here we go. It's time for some surface integration. Haven't done this kind of stuff in a while, so let's see if we can still do it. In general, we know that if we're given some surface integral in this form without without any force or vector fields in the integrand, we can set it up as the double integral over the xy projection of our region with whatever we have in our integrand here. In this case it's z. Then we have to multiply by the square root of zx squared plus zy squared plus 1, and then we are done. So let's figure out what this is going to be. Zx is going to be x over root x squared plus y squared, whereas zy is going to be y over root x squared plus y squared. So setting up this integral, we are going to see that zx squared is just going to be x squared over x squared plus y squared, and zy squared is just going to be y squared over x squared plus y squared. So z times the square root of these two added together is just going to be x squared plus y squared over x squared plus y squared, which is just 1. And then we have to remember that we already have a plus 1 in here, dA. And then finally, it's looking like, since we know that we're going to be taking a look at the xy kind of shadow of this cone from z is equal to 0 to z is equal to 1, that's just going to be the circle with radius 1. So instead of replacing z with x squared plus y squared to the 1/2, we know that that's just going to be r squared, to the 1/2, which is just going to be r. So now we can change this to a polar integral, r dr d theta, where r runs from 0 to 1 and theta runs from 0 to 2 pi. We aren't bounded on on theta at all, so we can replace that with a 2 pi, and we are good to integrate as long as r squared root 2, as long as I rearrange things. dr. Okay, this is going to be 2 root 2 pi times the quantity r cubed over 3 evaluated on 0 to 1. Well, that's just going to be, let's see, 1/3. And so now we have a final answer of 2 root 2 over 3 pi. Let's compute this surface integral where S is a triangular region with these vertices. Well, let's get some axes in here, x, y, z, and let's plot them. 1, 0, 0, 0, 2, 0, and 0, 0, 4. So we're dealing with this area in here. So we know that if we want to do the surface integral, we're going to need to get the equation of this plane here, because we need a zx and a zy. Right now, we have no idea what those are going to be. Let's see, this intercept is 1, 2, and 4. So this is the way that I think through making one of these plane equations. If you have your own way, as long as it works, I really don't care. So when x and y are equal to 0, z must be equal to 4. Then we take a look at the slope running down z towards x, and we see that that is a slope of -4, so -4x. And in terms of y, heading down from our z-intercept, that is a slope of -2. So there is our z. Now we can find, that's our equation of this plane in terms of z equals. So now we can find zx, that's going to be -4, and zy is going to be -2. So this integral we can express as the double integral over the XY projection, and I really wish there was a better thing to say than that. It's starting to annoy me the number of times I have to that I say the XY plane projection of whatever. So I don't know how to avoid it though, because I'm not really sure if writing RDA is completely correct here. But as I don't particularly care. If someone knows something better to say, please let me know, because I'm getting a little tired of it. So this is going to be the double integral over r, where r is in the xy plane, of x, and then we know that we need root zx squared plus zy squared plus 1, and this is just going to be 16 plus 4 plus 1, which is root 21. And I'm actually going to move this out here. So now, since we want the xy, yx, there we go, we want this in terms of x and y, well, what we really can do over here is just disregard z, but also we can graph this. So we know that x has an intercept at 1 and y has an intercept at 2, and so the line defining that is going to be y equals 2 minus 2x. And so we can go dy dx, and we see that if we want this region here, the line, the equation y equals for the line that defines the lower boundary of this region is just y equals 0, and the line that defines our upper boundary, well, we already found that, that's just 2 minus 2x. And then in terms of x, we just want our extrema, so that's from 0 to 1. So now integrating, we have, whoops, so what I wanted to do, we have no y's in here, so our first step in the end is just going to multiply 2 minus 2x in here. So we are going to get 2x minus 2x squared dx for our final integral, and that's going to be x squared minus 2/3 x cubed on 0 to 1, which is 1 minus 2/3. So overall we have 1/3 multiplied by the root 21 we had sitting out there all along, and that will give us our root 21 over 3. Okay, a surface S is the graph of z equals h of xy equals xy above a region D. If the surface integral of xyz ds is equal to g of xy dx dy, then what is g of x and y? So pretty much they're saying, okay, rearrange this integral, don't actually compute it, but we need to make sure that you know how to go through the steps. So we're taking the integral of x, y, z over s ds. We know that in order to turn this into an integral over d, we need to replace this ds with a square root zx squared plus zy squared plus 1 dA, effectively. So we can find this. Zx is just going to be y, and zy is going to be x. So we can set this square root up as x squared plus y squared plus 1. And since we want to turn this into an integral over dx dy, we need to get rid of this z in here, which we can do because we see that z, that's a terrible error, z is equal to xy. So this whole integral is going to turn into the integral over r of xy root x squared plus y squared plus 1 dx dy. And we see that if we take x squared y squared and stick it in here, we will get the double integral over r of the square root of x to the 6th y to the 4th plus x to the 4th y to the 6th plus x to the 4th y to the 4th dx dy. And that right here is our answer, because they're looking for this function g of x that is going, all of it, everything that's going to be sitting inside there. So that's answer choice C. let's express the area of the surface given by the graph of this thing over the triangular region D with these vertices. So when you see something like this, and you've got all this crap in your integrand, it's worth taking a look at whether every single region of integration, so your bounds on all of our integrations, if all of those are different. Because if they are, all we're really doing here is setting up a double integral. And in this case, yeah, every single integral has different bounds on integration. So we can set our graph up and graph these points. So we have 1, 0, 1, 3, and 4, 3. So we're dealing with this triangle, and for once, I bet it annoys some of you, I'll actually put my ordered pairs. And 4, 3. And yeah, we want this region here. So it looks like all of our integrals are expressing things in dx dy. So let's figure out those bounds. If we draw a line parallel to the x-axis, it's going to enter our region with the line x equals 1. So our first integral should have a lower bound of 1. That rules out d and c and a. Wow, already down to a 50-50. And then we see that we are leaving this region along this line, which, let's see, I've drawn it like it has a slope of 1, but does it actually? Yes, it does have a slope of 1. So this is going to intersect at y equals -1. So this is y equals x minus 1. And because we're doing our integral dx, we need this in terms of x equals, so our upper bound should be y plus 1. And that just confirms what we see up here. We see y plus 1 in both of these. But if we take a look at our bounds on y, well, y begins at 0 and ends at 3. Those are just our mins and maxes. And so b is out, and e is our answer. Let's let S be the portion of this surface that lies within the cylinder of radius √3, and we're finding z plus 1 ds. So we know that ds is going to get replaced with the square root of zx squared plus zy squared plus 1. And since we already have things in terms of z equals, this is pretty easy to figure out. That zx is just going to be y, zy is going to be x. And so our integral, well, our integrand is going to end up being x squared plus y squared plus 1. And then we see that we already have a z plus 1 out here. And since we know that we're taking, we want this to be an integral over r dx dy, or maybe it'll end up being a polar integral, we don't know, so let's just keep that as dA. We want to get rid of this z because we're only dealing with x's and y's in this integral. So we know up here that z is equal to xy. So we are going to have xy plus 1 right there. So this is looking like a pretty ugly integral, but we know that we're within this cylinder, so we can set this up in polar coordinates because this surface is defined for all xy, and so we are going to take up the entire kind of footprint of the cylinder, which is just going to be a flat circle of radius √3. Okay, so let's turn this into polar coordinates so that we can evaluate it. Our bounds end up being pretty easy because we know that we're just within the cylinder of radius √3, so r is going to run from 0 to √3, r dr, and then our theta is going to run from 0 to 2 pi because we'd like to have the entire circle over here. Okay, but it gets pretty ugly when we've got to replace everything else. So this is going to be, let's see, r squared sine theta cosine theta plus 1. And I'm going to have to move this out because we've got so much stuff, times the square root of r squared plus 1. And as you can see, this thing is super ugly, and we're going to need a bunch more space to deal with it. But as you'll see, in the end, it's actually not too bad. Let's split this up into two integrals. If we distribute this thing out, we're going to end up with r squared sine theta cosine theta, multiply by this, multiply by r, and we'll also end up with 1 times this times r. So we can express this thing as the integral from 0 to 2 pi and the integral from 0 to root pi of r cubed sine theta cosine theta root r squared plus 1 dr d theta. And then to that we're adding the integral from 0 to 2 pi and the integral from 0 to root 3 of, well, that's just going to be r root r squared plus 1 dr d theta. And at this point, it would be very, very nice if, this thing ended up being this whole integral worked out to 0. And in fact, it is our lucky day. So let's reorder this integration, which we can do without messing anything up, and let's just take a look at the inside integral with all of our constants moved out. So you'll see what I mean. So we can rearrange this as the integral from 0 to root 3 of r squared root r squared plus 1, r cubed root r squared plus 1 times the integral from 0 to 2 pi of sine theta cosine theta d theta. And we will see that this thing can be replaced in here with, let's see, sine theta cosine theta. We know that that's equal to 1/2 sine 2 theta. And so just taking a look at this inner integral, we can rewrite this as the integral from 0 to 2 pi of 1/2 sine 2 theta d theta, which is going to evaluate to negative 1/4 cosine 2 theta on 0 to 2 pi. And this is where the magic comes in, because we're going to get a multiple of 2 pi and or 0 in both cases for this cosine. This is going to work out to, let's get some more space in here, 1/4 times the sine of the cosine of 4 pi, negative 1/4 times the cosine of 4 pi, which is just 1. And over here, negative 1/4 times the cosine of 0, which is just 1. So because this, we can get rid of that because we know that this thing, that inner thing, because we got the same thing for each, when we evaluated, we got the same thing for each bound. This entire inner integral, and I might want a dr to close this thing out. This entire inner integral is 0, so it doesn't matter what this outside thing is at all. So we can get rid of it completely. And up here as well. So now all that we're left with, since we know that this is essentially 0 plus that, all we have to do is evaluate this. This is just going to be 1/3 r squared plus 1 to the 3/2 on 0 to root 3. Let's see, root 3 squared plus 1 is going to be 4. 4 cubed is 64. Root 64 is 8, so this is 8/3. And right here we're going to get 1 to the 3/2 times 1/3, which is just 1/3. So now we have 7/3 on 0 to 2 pi d theta, which is just our 14 pi over 3. I really like this question, actually. It's one of those nice times where something really disgusting gets set up, and then you realize that you really don't have to do it, which is always a great feeling. Let's find the area of the portion of this plane that lies in the first octant. So we're going to practice doing this without graphing anything out. All we need is this in terms of z equals. Well, we can say that 2z is equal to 2 minus x minus 2y. So we can say that z is 1 minus x over 2 minus y. So our zx and zy are going to be negative 1/2 and negative 1 respectively. So our big square root is going to be 1 plus negative 1 squared plus negative 1/2 squared. And that's going to give us 2 plus 1/4, which is 9/4, which evaluates to 3 over 2. So we can take our original integral, which was the double integral over s ds, and we can turn this into the double integral over r of 3 over 2 dA. So now we got to figure out what our region is actually going to be. We want the xy projection of this thing, so we're just going to set z equal to 0, and we will see that x plus 2y is equal to 2, which is nice because we can express this in terms of either x and y, but let's do it in terms of x for now. So this is going to be x equals 2 minus 2y. And we know that'll be our upper bound for x, and since this is just a plane that is positive in the first octant, that's you know, if we were to graph this out, even though I said we weren't going to graph it, it helps a little bit. It's going to make some kind of triangular region in here, and so we know that both x and y are going to be bounded on the bottom by 0, because if we draw a line parallel to either x or y, you can see that this region, if we neglect this z, we could redraw this, its shadow on the xy plane, and in fact I will graph this. This is going to be, let's see, 2y equals 2 minus x, so y equals 1 minus x over 2, so 1, 2, and that's going to be our region right there. And so you can see our lower bounds are 0. So we can put those in. Let's integrate dx, dy. We can move the 3/2 that we had over here outside of everything. And we are going to have our upper bound on x as 2 minus 2y, and our upper bound on y as our extreme value for y, which is just 1. So now, making some room over here, we can evaluate this thing. That we just have a 1 sitting in here. So since this first step doesn't have any x's in it, we're just going to multiply 2 minus 2y into here. And for our final integration, 2y minus y squared on 0 to 1 is just 2 minus 1, or 3 over 2. Okay, let's find the surface area of the part of this paraboloid that lies between the cylinder of radius root 8 and the cylinder of radius 24. So all we're going to need for this is our square root of zx squared plus zy squared plus 1, and we can turn it into a rectangular integral on the xy plane, and in this case we're going to be doing a polar integral. Zx is x, zy is y, so this is just root x squared plus y squared plus 1. Here we go. So we can set up our integral. We see that we want r to run from root 8 to root 24, and we want theta to run from 0 to 2 pi. And our integrand is going to be r dr d theta, and then we want our root, well, this is just going to be r squared plus 1, sitting in there. Now all we have to do is evaluate. This is going to give us, well, first off, I shouldn't get too far ahead of myself. This whole thing, we're not dependent on theta, so 2 pi is just going to go right out there. So this is going to be 2 pi times the quantity, 1/3 r squared plus 1 to the 3 halves on root 8 to root 24. And this works out very nicely because root 24 squared plus 1 is 25, which to the 3 halves gives us 125 over 3. And then over here, root 8, that's root 8 squared plus 1 is just going to give us 9 to the 3 halves is 27, which is going to give us 27 over 3. 125 over 3 minus 27 over 3 is just going to give us 98 over 3. 2 pi times 98 over 3 is going to give us 196 over 3. If S is the part of this paraboloid, where Z is less than or equal to 4 and N is the downward pointing normal, and F is this thing, then then find this integral here. So this, I hope you recognize, is not a surface integration question. So feel free to skip to whatever the next question is if you're just here for the surface integral. This is a flux integral. But in case you're up for it, I think I'll just do it anyway. I don't know why I put it on here, and I'll make sure to go change it. Yeah, I think it was very late at night when I made this PDF. So we need to find an F and an N. We're given our F here, and we know that the normal vector, when we have it in the form z equals, is just going, and specifically the downward pointing normal vector is just going to be zx, zy, 1. Sorry, -1. And so we can find this. Zx is just going to be 2x, zy is 2y, and so we can set this up as the double integral over S of, let's see, n, I should, yeah, well, we'll just put it in here, of n, which is going to be 2x, 2y, -1, and our f, which is x, y, z. But hold up a second, because we don't want a z in here, because we know that we're turning this into a double integral in the form, well, in this case, it's going to end up being a 2D polar integral. So we don't like that there's a z in here. But we see that z is equal to x squared plus y squared. So there's our saving grace. Up here, we can replace this with x squared plus y squared ds. So in taking this dot product, it's going to take us to the integral over r of 2r squared plus 2y squared minus x squared minus y squared. So that's just x squared plus y squared dA. And since, let's see, we are looking at the 2D shadow of this thing right here, when z is equal to 4, we are looking at our shadow is going to be the circle of radius 2, and when z is equal to 0, we're looking at a point here. So overall, we're integrating over this region right here. So that's going to give us r squared r dr d theta, where r runs from 0 to 2, and theta runs from 0 to 2 pi. So r cubed, evaluate on z, sorry, I'm really rewriting what we have here. I should kind of scrunch this together. There we go. So this is going to be equal to 2 pi times the quantity r to the 4th over 4 on 0 to 2, which is just going to give us 16 over 4, or 4. So 8 pi is our answer there. Let's let S be the part of the surface z equals xy plus 1 that lies within the cylinder of radius 1, and let's find the area of the surface S. So pretty standard question, very similar to a lot of the other ones we found. We need a zx and a zy. This is just y, and this guy is just x. So we can replace our integral, which was originally s, the double integral over s of 1 ds. We can replace this with the double integral over r of root x squared plus y squared plus 1, because we know that we're using these guys to replace our ds with zx squared plus zy squared plus 1 dA. So there we go. And we see that we're just within the cylinder of radius 1, and we're just looking at the xy projection of this. So this is going to be the integral from 0 to 1 and the integral from 0 to 2 pi of r times the square root of r squared plus 1 dr d theta. We're not dependent on theta, so we can get that out of there. I think one of these days I'm going to get too tired of doing that little extra step and just stop doing it and start just putting it there. But that day is not today, so if it helps you, I'm glad. So this is going to be equal to 2 pi times the quantity. Whoops, didn't mean to delete all that. 1/3 r squared plus 1 to the 3 halves on 0 to 1. And this whole thing, I kind of didn't give myself any space here. Well, evaluated at 1, this is going to be 2 to the 3 halves, so 2 root 2 over 3 times 2 pi. So 2 pi times 2 root 2 over 3. And then evaluated at 0, we will get 2 pi over 3. So overall, our answer is 4 pi root 2 over 3 minus 2 pi over 3, which is right there. Let's find the area of the part z equals 1 plus x plus some ungodly y thing that lies above the square with these vertices. So that's just going to be, I guess you could call it our unit square. 1, 1. So we're just dealing with that region, and we know that our final integral is going to be over 0 to 1 dx dy, because we're just looking at the shadow down onto the xy plane. And they're being nice to us. They're giving things to us in the form of z equals. So we know that we can turn this into the double integral that we want with the square root of zx squared plus zy squared plus 1. And since it's already in the form z equals up here, these are going to be pretty easy to find. So we're going to get zx being equal to 1 and zy being equal to, well, we're going to get 3 over 2 times 2 over 3 root y. That's just going to be 1 root y. And so this thing up here is going to become 1 squared plus root y squared plus 1, or just y plus 2. And so we can stick this in here. Y plus 2, that's a terrible 2. That looks like a C. Y plus 2 dx dy. And this is great because we're not dependent on x at all. So all this integral is going to do is just multiply the whole thing by 1. So we're left with a single integral. This feels like Calc 1. This is going to be equal to two thirds times y plus 2 to the 3 halves on 0 to 1. And evaluating this, we will get 2/3 times 3 to the 3 halves and 2/3 times 2 to the 3 halves, which we can write as 2/3 times 3 to the 3 halves minus 2 to the 3 halves. And again, Absolutely terrible 2 down here. But that's okay because our answer choice is up there and it's answer choice C. Okay, let's find the area of this surface given by z equals x squared plus y on all this crap over here. So this is, getting to the end of these questions or these sets of questions. I like to kind of speed things up a bit, like you would encounter or you would feel like doing in an actual exam. So let's do these last few pretty quick because the steps that you do for these are very very set, and as long as you have things in the terms of z equals, really you're just going to end up with a pretty normal rectangular or polar integral most of the time. So we see that our square root of zx squared plus zy squared plus 1 is going to be 4x squared plus 1 plus 1, which is just 4x squared, plus 2. And now we can just set up, whoops, that was, we can just set up our integrals. Dy is going to run from 0 to 4x, and we want to put that inside because we need to be able to u sub this, and dx runs from 0 to 11. Okay, I wrote 11 here and went through the whole thing, and I was getting 486 to the 3 halves, and I tried to evaluate that, and did not go well, but I misread up here. It's just x between 0 and 1. So this whole thing is going to be equal to 1/3 times 4x squared plus 2 to the 3 halves, evaluated on 0 to 1. This is going to give us 2 root 2 over 3, and this is going to give us up here, 6 root 6 over 3, 6 root 6 over 3, which we can express as 2 root 6 minus 2 root 2 over 3, which is answer choice B. And again, I've absolutely no clue where this question comes from. I haven't done it before. I don't know why it's here. I don't know where I got it from, but hey, it's good practice for me. Okay, question 7. Let's find the surface area of the part of this paraboloid that lies above the xy plane. So, same kind of thing. We're going to kind of blaze through these last couple. Zx is negative 2x. Zy is negative 2y. So we're going to get 4r squared plus 1, saving a little bit of time because this is going to end up being a polar integral. And since if z is equal to 0, this is the circle of radius root 2. We can set this up from 0 to root 2 and multiply all that by 2 pi dr. So, okay, we are going to get 2 pi times the quantity. Let's see. Two-thirds times 1/8 4r squared plus 1 to the 3 halves, evaluated on 0 to root 2. Here we're going to get 1 over 12, and we can take this out here as pi over 6. And so now evaluating root 2 squared times 4 is going to give us 8, plus 1 is 9, to the 3 halves is 27, and over here we're going to get 1. So 26 pi over 6 is going to be equal to 13 pi over 3. And yet again, I think it might be because it's like 11:40 at night and I'm pretty tired and I'm kind of losing my mind, but I don't know where this question's from. I'm kind of going insane. It's probably from exam 2, and it's just been it's been a while since I've seen any of those. Okay, here we go. Another one. Zx is going to be 3. Zy is going to be 1. So this is going to be root 3 squared plus 1, or root 11. And we are going to be looking at the shadow. Oh, okay, above the xy plane bounded by these guys. So we have two nice bounds on y. Y is equal to 0 and y is equal to x cubed, and we have x equal to 1. And because let's see, y is equal to x cubed and y is equal to 0, then our lower bound on x is 0 equals x cubed, or just x equals 0 dy dx. So this, because we don't have any y's in here, this is just going to multiply an x cubed in. X to the 4th over 4 on 0 to 1 is going to give us 1/4, and so we get root 11 over 4 as an answer. Okay, let's find the surface area of the portion of this parabola. Note to self, when z is equal to 0, our shadow is going to be x squared plus y squared is equal to 11, or just the circle of radius 11. But we see that we're bounded below by z is equal to 2. Okay, so we gotta revise things a little bit. If we're bounded below by z is equal to 2, well, we're going to have this parabola opening down, but bounding it by z is equal to 2 is just going to give us 2 equals 11 minus x squared minus y squared. And so we are going to get a circle of radius 3 in the form x squared plus y squared equals 9. Now all we have to do is find our root zx squared plus cy squared plus 1. Well, zx is just going to be negative 2x. Zy is going to be negative 2y. And yeah, we can solve this. So setting up our integral, we know that we want to go from 0 to 2 pi on theta and 0 to 3 on r. R dr d theta, where we have root, well, this is going to be zx squared, which is 4x squared plus 4y squared plus 1, where this can all be replaced with 4r squared, and then our r can head out here, where we're more used to seeing it. And now doing our integration, we are going to get 2 pi times the quantity 2/3 times 1/8, so just 1/12, which we can move out here as pi over 6 times the quantity of 4r squared plus 1 to the 3/2 on 0 to 3. And this is going to, for r is equal to 3, we are going to get 3 squared times 4, which is 36, so 37 root 37. And for r is equal to 0, we're going to get 1. So here is our answer, pi over 6 root 37, pi over 6, 37 root 37 minus 1. And finally, let's find the area of this thing. Let's see if we can do it in like 30 seconds. So, okay, setting z equal to 0, we're going to get 3x plus 2y equals 6. We can put this in the form y equals, if we say y equals 3 minus 3/2 x. Okay, that's good. So we can set up an integral from 0 to 3 minus 3/2 x, and from 0 to 2 on x, dy dx of, well, zx squared is going to be 9, zy squared is going to be 4. So we're going to have, let's see, 13, 14, and we're done. But let's just make sure. So root 14 is in here, and because that's annoying to deal with, we're going to move it over here. Root 14, we have no y's, so this is all going to get multiplied in. 3 minus 3/2 x. So integrating, we're going to get 3x minus 3/4 x squared on 0 to 2. This is going to give us 0. This is going to give us 6 minus 3/4 times 4. So 6 minus 3, which is 3, times root 14 is 3 root 14. And we're done. Ugh. Okay. Okay, I've got some editing to do. There were some issues. I had to blow my nose. I had to cough a couple times. You don't get to hear any of those coughs, but hope that was helpful. I know for a fact that going through every single question for specific topics, is incredibly helpful for me, at least on the recording side, because it forces me to, get back in the groove of, okay, this is how this is how these questions work. This is how they work every single time, or this is how, like, the three different ways that they can possibly work. And just seeing that and getting that back in my head is very, very helpful for me. And I hope it is for you too. And since people actually watch these things, I'm assuming that that's a yes.